Alright guys, so to continue our discussion dealing with intermolecular or interparticle forces, we're going to look at the different types of solids that form and what forces are in those solids themselves. With solids, we have two major types of solids. We have amorphous solids. These have a lot of disorder in their structure, so we mentioned these before. These are things like glass or plastic, that the particles are not in nice orderly like rows and columns. And then we have crystalline structures. These have a regular arrangement of their components in their structure, so the atoms are going to be in even rows, columns, and very orderly overall. Majority of what we deal with are going to be those crystalline solids. Looking at crystalline solids, we say these are made up of a lattice. So think of if you have a lattice fence, there's multiple pieces of wood connecting to create that lattice. Same kind of thing occurs here, where a lattice is a three-dimensional grid that describes locations of the pieces in a crystalline solid. So every particle is going to be attracted to every surrounding particle. Typically, the smallest repeating unit we refer to as the unit cell. You guys are not going to have to worry about identifying unit cells, but this is where whenever we are looking at the particulate level at something, we are typically looking at its unit cell, of how these particles are arranged, and their arrangement can affect their properties. But you guys do not need to know the different types of arrangements or be able to identify them. I just want to show you that there are different arrangement for different structures. So here's some examples of where you may have more particles within the same amount of space, and it would have a greater density. Sometimes it's more of like a square arrangement versus a hexagonal arrangement, depending on what we're dealing with. And like I said, you guys do not need to identify these at all, but this is just showing you how that simple unit is built up to make a larger 3D structure. So that's an example of a very simple one. Here's a body-centered one where there are more particles within the same given amount of space. And then here's an example of a face-centered cubic where we have even more particles within that same given amount of space. So notice that it becomes more dense as we kind of increase the number of particles in that given amount of space. But yet again, I said you guys are not going to have to identify these. I just wanted you to be aware that not everything is arranged the same way. Looking at our types of crystalline solids, these are ones that you'll have to know and be able to identify based off of the formula. And you'll see this with our crystal type worksheets that you're going to go through. Our first type of crystalline solid are our ionic solids. These are going to be our solid ionic compounds. So all of those individual lattice points where they're connected is going to be an ion. So you have ions attracted to every surrounding ion. We're also going to have molecular solids. These, remember, are made of molecules, so it only has nonmetals. These we're going to have polar molecular solids and nonpolar molecular solids. So you will have to look at the actual formula to determine if it is going to be polar or nonpolar. We also have atomic solids, and with these we have metallic solids. These are where the metallic crystals have those positive metal ions and then the free floating electrons. We have non-bonding atomic solids, which the individual particles making up that lattice are going to be atoms. And then one thing we have not talked about yet is we're going to have network solids or network covalent solids. These have a multitude of covalently bound atoms, which due to the number of bonds, it ends up being very strong. So let's look at the ionic solids. Here we said these are going to be our ionic compounds. So particles are held together by the attraction of opposite charges. So you have those alternating positive and negative ions, and each ion is attracted to every surrounding ion. With these, they have large melting points and boiling points. So that's why these are going to be solids at room temperature for us. And the particles are in those lattice positions, so the samples do tend to be very hard and very brittle. So these are not flexible. If you hit them with a hammer, they will crack and shatter. They're not going to alter their shape. And every electron is locked in place in an ionic solid. So that's why these are not good conductors as solids. Remember, ionic things only conduct in the aqueous or liquid form. So any ionic compound as a solid is going to be considered an ionic solid and have ionic bonds within it. We also have our molecular solids. So with molecular solids, we have molecules occupying those individual lattice points. And depending on the type of molecule is going to depend on what type of intermolecular force or interparticle attraction is within that molecule. So with these, we said we have nonpolar molecular solids, and then we have polar molecular solids. For the nonpolar molecular solids, the only forces we have are those dispersion forces, or like the LDFs for short. And remember, LDFs are London dispersion forces. The strength depends on the polarizability. And remember, polarizability was determined by the number of electrons. The more electrons, the more polarizable, therefore the stronger those London dispersion forces. These tend to have very low melting points and boiling points, so majority of them are gases under standard conditions. So that 25 degrees Celsius is approximately room temperature. So these are going to be gases at room temperature. With polar molecular solids, these typically have like the dipole forces. They can also have London dispersion forces. And if it has hydrogen with one of those very electronegative elements, it can also have hydrogen bonding, depending on what is bonded together. Those dipole forces in polar molecular solids are generally stronger than the dispersion forces. And we say generally because there's always going to be an exception. You may come across something that has a lot more electrons, and therefore the dispersion forces can overcome the dipole forces. That would only come up in specific questions where they want you to justify why something with only dispersion forces may have a higher melting point than something that also has dipole. But typically, anything with dipole forces is going to have a higher melting point and a boiling point than something just with London dispersion forces. Typically, hydrogen bonding is going to be stronger than dipole forces as well. And generally, no matter how strong those intermolecular interparticle forces, it is always much, much weaker than the actual forces in bonds. So remember, we said ionic bonds, covalent bonds, metallic bonds are still going to be stronger than these interparticle attractions. Let's look at metallic solids. So like we said, this is going to be solid metal. Like if you had a sheet of aluminum foil, that is an example of metallic solid. So these are our electron C model. So remember we have our cations with that C of mobile valence electrons. So the valence electrons are able to move around rather easily. So the electron C model accounts for the different properties of metals. So we already talked about with metals, they do have high melting points and boiling points. They tend to be solids at room temperature. We've also mentioned that metals tend to be malleable and ductile. So remember, malleable means that it can be hammered into sheets. Ductile means it can be drawn into wire. So since those cations are not attracted to one another, they can move around in relation to one another. So they can rearrange to form a flat sheet or to form a wire. Metallic solids, because of those mobile electrons, they are good conductors of heat and electricity, because since the electrons can flow, heat and electricity can also flow. These also have the high melting points. That's why they were solids at room temperature. And within the metallic solid, the internal bonding, so the bonding between the individual cations, it has to be both strong and non-directional. So a single cation is attracted to all of the surrounding electrons. And then the cation next to it is attracted to all of the surrounding electrons. So it's not only attracted to one particular electron. Something new we have not talked about yet are non-bonding atomic solids. This is where on occasion we can have a noble gas typically, or an element that is an atom by itself that is a solid. This is fairly rare, but we can have stuff like solid krypton if we're at certain temperatures. That is considered a non-bonding atomic solid. So these are things that are non-metals. The only forces present are going to be those London dispersion forces, the LDFs, because it's a non-metal and there's no bonds going on. And remember, LDFs, their strength depends only on polarizability, so the number of electrons that are in that substance. So one thing that we mentioned in Chem 1, but we did not do a lot with, were network covalent solids. These are things that you may be familiar with, but you may not know how they form necessarily. But with network covalent solids, the individual points of the lattice are individual atoms, and the atoms are held together in a three-dimensional network by covalent bonds. So it's only going to be using non-metals, and not everything can make network covalent solids. But you may have a carbon attached to 4 other carbons, and all 4 of those carbons are attached to additional carbons, and it makes a larger structure. There are very few examples of network covalent solids. These are ones that you should memorize and be able to recognize if they come up. These are going to be things that are strictly carbon based. So like it might say carbon and it might say diamond or graphite next to it, but it is only carbon based. There's nothing else there. That is considered a network covalent solid. If we have solid silicon, that is a network covalent solid. There are a couple of compounds with silica. If we have silicon dioxide, that is quartz, like the crystal. That is going to be a network covalent solid. And then if we have any silicon carbides, those are also network covalent solids. So you should remember any form of solid carbon, solid silicon, silicon oxides, or silicon carbides will be network covalent solids. So here's what they look like. So here's an example of the quartz, the silicon dioxide, where we have silicon dioxide that is attracted to and attached by covalent bonds to other silicon dioxides, and it makes this large three-dimensional structure where there is a multitude of covalent bonds. This also, like we said, is very common in carbon. So with carbon, there are many types of solid carbon. We have coal, which is one of those amorphous solids that is not a nice orderly pattern. We also have diamond. Diamond is just a large 3D structure of carbons bonded to one another. It is the hardest natural substance on Earth. It insulates both heat and electricity. And then we also have carbon that is graphite. Graphite is what is in your pencils, so like your lead for your pencils. We tend to say graphite is rather slippery. I'll explain what I mean with that in a moment, but the particles are able to slide past one another. And graphite can actually conduct electricity due to the way it is structured. One that we're not really going to deal with is fullereness. These are strong, good conductors of heat and electricity. These are going to be more tube-like structures of carbon. So I'll show you what that looks like in a moment. All of these, since they are all carbon, but there are different forms of carbon, these are referred to as allotropes. So allotropes are different forms of the same element or same compound. So looking at diamond, whenever we look at the diamond structure, you have a carbon attached to 4 other carbons. So each carbon is sp3 hybridized and connected to 4 other carbons. But then all of the other carbons are attached to additional carbons to make these large structures. So because there's so many covalent bonds, we have a strong array of those sigma bonds. Because of the number of bonds and how they all bond to one another, that's what makes diamonds so hard. They're at the top of the Mohs hardness scale. This we deal with more in earth science with rocks and minerals. Remember, hardness refers to the ability to scratch another object. Diamonds can scratch anything. And diamonds also have a very high melting point. So even though it's made of covalent bonds, which are typically weaker than ionic bonds, because of the number of covalent bonds that there are in the structure, it has a very high melting point. And like I said, these do not conduct electricity because electrons are not free-flowing and able to move in this structure. Whereas when we look at graphite, so graphite is an allotrope, it is all carbon, but instead of a carbon being attached to every other surrounding carbon, we end up with these carbon sheets that align with one another. So each carbon is connected to 3 other carbons instead of 4 other carbons. So they are sp2 hybridized. Because of that, it creates those flat sheets of 6 rings, like hexagons, with 120-degree angles throughout. So you have these individual layers of carbon overall. Those non-bonded hybrid orbitals will overlap and make pi bonds, which, remember, pi bonds are weaker than sigma bonds. Because of that, it is going to allow those sheets of graphite or sheets of carbon to slide past one another. So the p orbitals overlap, forming a pi network. So you end up with these individual sheets, and then these pi networks are the ones shown in blue, where it's basically layers of an electron cloud. Electrons are free to move throughout those individual orbitals, which means that since electrons can move around, it can conduct electricity, and those layers, since they're not attached to one another, can slide past one another. With fullerness, these, like I said, is another structure of carbon. This is going to be a spherical, elliptical, or hollow tube. There's different forms of this. Here you can see a spherical version of fullerness. Looks very similar to a soccer ball structure, where you have all of these ring structures that are connected. But we can also have this as a tube structure, where it creates these nanotubes that are hollow, but you have those, yet again, those ring structures around the outside. Part of going through the crystal types worksheet is making sure that you can match up what type of crystal a substance has and what type of interparticle attraction we're going to have with it. So looking at the types of crystals, we said we have ionic crystals. Those are primarily going to have ionic bonding. I apologize, I'm writing with the trackpad of the computer. We said we have metallic compounds. Just going to put met for metallic. Those have metallic bonds. With the molecular solids, remember we have nonpolar molecular solids, and then we have polar molecular solids. And I'm going to put MS for molecular solid. Nonpolar molecular solids only have those London dispersion forces, only have the LDFs. And remember, their strength is determined by that polarizability. Polar molecular solids will have dipole forces, as well as LDFs, because LDFs are going to be in everything that have electrons, essentially. But these could also have hydrogen bonding, depending on what our actual atoms are. So not everything that's polar will have hydrogen bonding, but that is an option depending on if we have hydrogen with that nitrogen, oxygen, and fluorine. We also mentioned we have the non-bonding metallic solids. Remember, those are going to be our things like if we have solid krypton. I don't think I've ever come across like solid oxygen, but that would still be O2. So it would have to be something that is not diatomic, that is not bonded to anything else that is a solid. These only have those London dispersion forces. And then if we have our network solids, remember, are held together by a bunch of covalent bonds. So that should help you address some of the things you're going to see on the crystal types worksheet, and we will review a little bit of this in class as well.